The labs are solubility within a family and a computer lab on molecular models. So for those of you that have completed all the labs and everything, you can turn in your lab notebook. Okay, turn in your lab notebook. Maybe in 2 weeks, I'll give a more firm due date, but if you turn in your lab notebook, I'll give you 100 points, and that just helps boost your grade. Okay. This audience, everyone here is mostly an A, so just add up to your A. So last week for lab reports, today is November 2nd. 2020. So labs last week. Lab notebook, something that's going to be due to be announced. Can you guys see this? Start working on quiz 4. I stubbed my finger here, and it just hurts with this grip. So see, I don't even think I can write properly. Okay, so quiz 4, you want to start working on that. That's when test 4 will be, and I'll give you a firm due date on test 4 this week or next week. Okay. Anything else? If you're still doing that clutch prep thing, okay, I don't know who isn't, but I got to report to them people, so help me out. I solicited them to help you, not just me, other chemistry professors, so they want your feedback. Make sure you do those drills. Quiz 4, lab report, lab notebook, and definitely watch the lecture. Watch Friday's taped lecture. Okay, last Friday was the 30th. Okay, so watch that tape lecture. The topics were quantum numbers and electron configuration. I can assure you, you'll see them on the exam. So because you'll see them on the exam or the quiz, I should ask you to watch it. And if you have any questions or comments, meet me in my office or in my Zoom office hours. A couple of people come to my Zoom office hours. It's very good. Okay, very low key. No need to worry about anything. Right? Topics are quantum numbers and electron configuration. Also, one thing that just came to my attention are your lab reports. Okay, so I want you to start turning in those lab reports. It's like a dump fire. Everyone's dumping stuff in. And I'm trying to keep pace with the grading, but definitely submit any lab reports that you feel are behind or lacking. The ones that I am going to grade this week are Hess's law and what was the other one? I think it's Boyle's law, right? Yeah. Okay, it's crazy. Okay. And then on this rotation, we're going to do solubility within a family, and then molecular models or Lewis structures. Okay, so that's in this rotation, and this is the last week for you to do solubility in a family. I think all of you have done it. All right. So this is more for the other sections. Right, so turn in those lab reports. I think since I'm teaching Chem 2, and I know I have some of you here, I'm not going to do the split thing. I think I'm going to just do Monday, Wednesday, Friday, every day new lecture. Okay. So, and I'm going to have a lab every week. Okay, so it's better for all of us. It's better for you also. Because last time I checked, there's only 12 students, so we can distance with 12 students, right? So I think that's more convenient for you, more convenient for me, and everything. This class originally had 24 students, then we split it to 12, and now 3, 4, 5. 5. Okay. Some sections I'm only having 3 or 2. So, all right, let me crash course you guys through chapter 8. And then the big one would be 9 and 10. So get ready for that probably next Monday. Okay, but watch the tapes. All right, so periodic trends. Couple of things I want to tell you guys. Going down is a group, right? Kind of know this. Okay, and some groups have very specific names. Some groups have very specific names. All right, group 1A, group 2A, then we go to the Bs. Okay, then we continue with the 3s, and then all the way to the 8s. So just going down, that's called a group. Okay, going left to right, okay, that's called a period. Okay, a period. So going left to right in the periodic table, that's called a period. Period gets designated by the letter N. So this is your electron configuration. This is another electron configuration. So going down, we have a group. Left to right is a period. And so we can call this period 1. Okay, for N equals 1. Okay, we can call this period 2. Okay, period 3. Period 4, period 5, period 6, period 7. Okay, so that's called a period. N is also called a principal quantum number. Okay, so you'll learn more about this when you watch last Friday's lecture. Hopefully you have last Friday's lecture. It goes into a little bit of detail what principal quantum number is, but this period is also that period energy level N equals 1, period 1, period 2, period 3, so on and so forth. Designates the row in the periodic table, and N is also known as the principal quantum number. They're sort of energy levels. N equals 1, then an N equals 2, then an N equals 3, N equals 4. Okay. Want you to know another thing, as N equals 1 is closer to the nucleus. Okay, what do you think energy level 2 would be? Farther, N equals 3 farther, N equals 4 farther, farther, farther. It's like energy levels. Like how many of you play a video game? Video games, right? Level 1, level 2, level 3, level 4. Okay, so level 1, level 2, level 3, level 4, level 5. Farther, farther, farther away from the nucleus. Another thing I want to tell you guys about the periodic table is the blocks. Okay, shown here we have the s block. So this would be the s orbital. Okay, right? Here would be what's called the d block, n-1 block. So as we go electrons, it's going to be electrons that will go to the 4s, and then from the 4s they're going to go to 3d. And then from 3D, they're going to go to 4P. So the electrons march in a very, very specific order. Okay, again, this is in reference to last Friday's tape lecture. So please, I ask you to watch that. And then this is called the P block. Okay. Yeah. So the electrons here, for these elements, occupy the P orbital. And then finally, though we're not going to be talking about this, this is called the F block. Okay, the lanthanides and the anthanides are called the F block. So the electrons go to the F orbital in the periodic table, where the electrons are housed. Okay, where the electrons are housed, very specific orbitals. Okay, where the electrons are housed. So going down a column is a group. Going across is a row. What else can we learn from the periodic table here? What else can we learn from the periodic table? One thing, the groups have a very specific, some groups have a very specific name. So group 1A, also this is called 1, depending on what version of the periodic table you're using. These are called the alkaline metals, and they're usually +1 in charge. Okay. There's group 2A, or some periodic tables call this group 2. Okay, these are the alkaline earth metals, and they have a charge of +2 as an ion. As an ion, okay, form ions that are +1, form ions that are +2. So specific groups have specific names. Not all of them, but some of them. And obviously being +1 means it loses 1 electron. Being +2, elements here like to lose 2 electrons. Okay, so lithium would like to be +1 as an ion. Sodium would like to be +1 as an ion. And lo and behold, if sodium becomes +1 as an ion, it loses that 1 electron. Sodium by itself, you see, has 11 electrons. Once it loses that 1 electron, it becomes 10, and it becomes noble. It has the same electron configuration as neon. So that's why these like to be +1. That's why these like to be +2. Something that we can get from the periodic table. Group 7A are called the halogens. Okay, some periodic tables call this group 7, and they like to be -1. Okay, they like to gain 1 electron. So chlorine by itself, 17 electrons, Cl minus, 18 electrons. It has a filled 3p shell. Completely filled 3p shell. So it becomes quote-unquote noble. Group 6A, or 6, they don't have a name, but they like to be -2 ions. They like to gain 2 electrons. Okay. Classic example of this is O-2, the oxide ion. Oxygen by itself is oxygen, but if it were to form an ion, it would gain 2 electrons. You see, if it gains 2 electrons, it becomes noble. Here it has a filled 2p orbital, 2p shell, is it not so? Right? It will have a filled 2p shell. If it gains 2 electrons, it becomes noble. Okay, finally, group 8A, or group 18 in some periodic tables, they call that the noble gases, very stable. Okay. Exceptionally stable, and okay, group 8A, group 18 noble gases, very stable, filled shell. Okay, filled shell. So as an example, neon would have, where neon is right here. Okay, it has electrons filling the 2s and then the 2p orbital, so it has a filled n equals 2 shell. Argon has a filled n equals 3 shell, right? 1, 2, 3. Krypton has a filled n equals 4 shell. 1, 2, 3, 4. Xenon has a filled n equals 5 shell. N equals 5 shell. 5s, 4d, and 5p are filled. 1, 2, 3, 4, 5. So it has a filled shell. So example, neon has a filled n equals 2 shell. So some things about the periodic table that we could guess, just automatic. You should be able to look at it and then see certain things, and that's what Chapter 8 is mostly about. I think I'm out of paper. There's a couple of other trends in the periodic table that I'd like for you guys to recognize and know. And there's 3 of them, actually, in this chapter. And let's go over them now. All right, so as a review, going down, we have a group. Going across, we have a period. And then some groups have very special names. And it's all about achieving nobility. Okay, it's all about achieving nobility. These guys can be noble. The transition metals, I should say, they can be all over the map with their charges. Okay, they can be all over the map. +5 here, +3. Iron is +2 in our blood, +3 elsewhere. So. Okay, what else can we gauge from the periodic table? Okay, one thing we can gauge from the periodic table is something called the effective nuclear charge. It's also called Z of F. Okay, and let me give you just a schoolyard definition, not a textbook definition, because I don't really know a textbook definition. But it's the charge an electron feels from the nucleus. Okay, mostly protons. Okay, in an atom. The charge an electron feels from the nucleus. The nucleus has protons and neutrons in an atom. So let me see if I can explain this. So here's our nucleus in green. Okay, what's housed in our nucleus? Protons, which are positively charged, and neutrons, which are neutral. We won't care about them. And what's circulating, orbiting, buzzing around? Wave particle density, what's buzzing around? Electrons, right? Yep, very good. Electrons. And electrons can be the n equals 1, n equals 2, n equals 3. Okay. Here's another orbital, n equals, I don't know, energy level 4, n equals 5. You can go on, so on and so forth. But you see, have here in our purple boxes, okay, I'm going to call this the outer electrons, also known as valence electrons. Okay, outer. And I'm going to call the electrons, let's put them here in this color. Let's put them in blue or black. Okay, we'll call these core electrons. Okay, very close to the nucleus. So, the charge an electron feels, you see the protons are positively charged, and they're going to attract. Okay, they're going to attract, but they're going to attract more the core electrons. Okay, so let's say I have another electron here, another core electron here. We'll put them in black. Okay, you see these core electrons are really, really, really attracted. Positively charged protons are really, really attracted to the electrons, but you see they're really attracted to the core electrons more than to the outer. Okay, so these outer electrons, what they do is they shield. Okay, this is also known as shielding. So these core electrons shield what we're going to call in the purple box the outer electrons, or the valence electrons. You know, it's like this. Yeah, I teach this class. Okay, so I am the nucleus. I am the nucleus of this class. Okay, you guys, I am the center of this. chemistry 1510. Really, I am the center. And you guys are literally, all around me are, let's say, electrons, since I'm the nucleus. So let's say I yell. Okay, let's say I'm lecturing. Let's say I'm screaming. Study hard. Okay, study hard. I scream it at the top of my lungs. Study, study hard. Okay, watch the lecture. Okay, do your quiz. Come to lab. Okay, who do you think feels that? You think Kimberly feels that? Or you think the guys in the back, Adriana or Joshua? Who gets that more? The core electrons, in this case, Kimberly. Okay, you guys in the back, you hear it, but you're more so the outer electrons. Okay. When I'm yelling and screaming, I am, after all, the nucleus. I am the instructor of the class, not to be so braggadocious. But if I'm screaming and yelling and getting mad and angry or telling you this or telling you that, okay, she's going to hear it more. Okay, she's my core electron. You guys out there, far away from the nucleus, the outer electrons. Okay, so that's how it works. Okay, shielding. You guys are shielded from me. Who shields you? You guys, Kimberly, and even you got a second row here, Harper, and you're also being sort of shielding the outside, shielding them. Right. So that is what shielding is. So this is the trend. Okay, as you go across a period in the periodic table, the shielding Z of F increases. Okay, there's more electrons, so more shielding, and also going outer and outer and outer. As you go down a group, okay, the shielding increases as well. So that's our first trend, shielding. Okay, the reasoning behind this, as you go here, you're increasing the number of electrons. Okay, and usually these d electrons, especially the p electrons, they're kind of, tucked in. So the core electrons are shielding more and more of these outer electrons. Same as you go down. Okay, higher and higher energy levels as you go down, n equals 1, n equals 2, n equals 3, n equals 4, so on and so forth. All right, so effective nuclear shielding increasing across a group, increasing down a group, increasing across a row. Right. The next one is going to be the atomic radius, the size of the atom. So this is basically the size. So, here's our atom. We'll pretend it's a sphere. Okay, just the size. Okay, the radius. All right, so the trend here is a little bit different. Here, the atomic radius increases the other way. This is the only one that is a little bit weird. The atomic radius decreases left to right, increases right to left. So here I'm having the increase going that way. So here the atomic radius increases. And then down a group, the atomic radius increases. Okay, so down a group, and then across a period. Okay, so what is the reasoning behind this? Okay, let's get our periodic table out. Okay, I'm just going to pick on lithium and sodium. All these guys, remember the atomic radius is increasing. So what do you think is happening as you go this way? Okay. Well, Let me ask you this. Group 1, lithium, sodium, potassium, what charge would they like to be? What charge would they like to be? Would they like to be +1? Yeah. So why would they like to be +1? Okay, sodium would like to be +1 because it would be noble. It will have the same electron configuration as neon. Potassium K would like to be +1, so it would have the same electron configuration as argon. So they, by sacrificing or losing that electron, they basically become noble. Okay, their electron configuration is of their nearest noble gas. So what do you think that electron for lithium, okay, where do you think that electron would be? Would it be like this? Or would it be here, take me, take me, take me? Okay, so I can be a noble gas electron configuration. How would it be? Like this? Or like this? It will be here, take me, take me, take me. Okay? So the electron configuration, for example, sodium is neon 3s1. Loses that electron, loses that 3s1 electron, it becomes a neon. It's very happy because it has a filled n equals 2 shell. So obviously it's going to be like this, okay? So if you're like this, are you bigger or smaller? You're obviously bigger, okay? So that's the reasoning why you have this situation that's occurring. Okay, these guys want to give the electrons. Okay, what do you think about these guys over here? Okay, this general window. Are they like here, here, take this electron, take this electron? Not only do they want to keep it, Antonio, but fluorine, chlorine, bromine, they want to take one. They take one, they become noble. So these guys over here, okay, they're more like this. In fact, they're like a snatcher. They're going to snatch electrons. Okay, so that's the reasoning why the atomic radius is going to increase. Yeah. The atomic radius is going to increase this way, but decrease the other way. Okay, so again, okay, look, take me, 1s1 electron. I'm a 3s1 electron. I'm a 4s1 electron. They want to go become noble. When they give off that electron, you see they lose that electron density. Okay, wave particle theory. So the atomic radius increases this way, and in other words, it decreases the other way. Right. So that's the general trend. Okay. Okay. Ionic radius. Okay, this is the radius of the ion. And basically, I think this is kind of makes intuitive sense. But if you're an anion and gain electrons, are you bigger or larger? Are you bigger or smaller than before? You're bigger. Okay. So anions are larger. Okay. What about cations? Okay. Cations are smaller. Why? Because they gave away the electrons. Gain electron density. And cations are smaller. Okay, they lose electron density. And that is the ionic radius situation. If you're an anion, right, you're going to gain electron density. And you become larger than before. All right, our next trend here is the ionization energy. Okay, we can do the first ionization energy, so we'll just do IE1. Because there's a second, there's a third, fourth ionization energy. So basically how we define this is again, let me just give you, I don't know, playground definition, not a textbook one. It's the energy required to remove an electron, literally strip it, take it away. Okay, so it's an energy required to strip an electron. Okay, you were just putting in energy, an input of energy. Here you're not exciting it, and then excites relaxation, emission. Okay, it's not that. You're literally taking an electron away, putting in enough quanta to liberate the electron. Technically, it's 1 mole of an electron of a gas, so that's technically, but if you want to get very specific, technically it's energy to remove 1 mole of an electron. Okay, from atom in a gas state. Okay, strip, remove an electron. Okay, so there's an IE1, removing 1 electron. There's an IE2, removing the second. IE3, removing the third, so on and so forth. It gets larger and larger. Okay, so the second ionization energy to remove the second electron is going to be greater than the first. The third electron energy is going to be greater than the second, and so on and so forth. So on and so forth. The reasoning behind this is because as you strip an electron, you strip an electron, you strip an electron, you strip an electron, okay, you're going to get to more and more of the core electrons. Okay, more and more of the core electrons. So what's the trend here? Okay, so IE1, the first ionization energy, it's an energy. Okay, lots of energy means lots of energy. Okay, the first ionization energy increases across a period. Okay, and here it decreases down a group, or it increases going down to up. But here I'm going to say it decreases down a group. So the first ionization energy increases across a period, and it decreases down a group. All right, so what's the reasoning behind this? So if it decreases down a group, okay, what is increasing as we go down the group in the periodic table? Okay, so we said the ionization energy decreases. The energy required to remove an electron decreases. So why is it decreasing? Okay, video game people? People who play video games, what's increasing as you go down the group in the periodic table? What is increasing? What is increasing here? Video game people. I played the Nintendo Super Mario, so level 1, and then what happens? Level 2. Then what happens? Level 3. Okay, level 4. The ionization goes down, but why? We're asking ourselves. We're probing, why does it go down? At level 5, what are we doing as we go to higher and higher levels? Okay. What are we doing? Okay, we're getting more outer and outer and outer and outer and outer and outer. Okay. So which is easier to steal from me, a ring or a necklace, if you're going to steal something? Probably a ring, right? You had to go in there and really invade someone's space. Okay. So yeah, to remove an electron, since these electrons are getting more outer and outer and outer and outer and outer, it's going to take less energy, and less energy just to get one, because they're just more out there. Okay, which is easier? Okay, me to get out through that window or Joshua to get out through that window? Okay. He's raising his hand. It's easier for him to get out through that window. Okay, he's more outer. Okay, he can escape. Okay, if this room was an atom, he can escape. Okay, because his energy level, let's say 1, 2. So he's n equals 3. And you, Kimberly, are n equals 1. You're a core electron close to me. You're hard to escape. Okay? You're hard to remove as an electron. So that's the idea why the ionization energy. It takes less energy for Joshua to be removed as an electron because he's just more outer. Okay, n equals 3 versus n equals 1, Kimberly. Right. Why does the ionization energy increase? Takes more energy. Okay, takes more energy as you go across a period. Okay, down a group it decreases. Why does it increase? Okay, across a period. Okay, what's happening to these electrons? What about the noble gases, which have a filled shell? Okay. Okay, if they have a filled shell, do you think it's easier for them to remove an electron? They're full. Okay, it's full. Okay, it's going to take a lot of energy. Look up the tables if you have spare time. Look up the tables of the energy that's in your textbook. Okay, it takes a lot of energy to remove an electron here because it's already full. Okay, it takes a lot of energy to remove an electron here because it has a 2s full and a 2p full. Okay, same thing with krypton. So that's the general trend. Same thing here. Okay, these guys like a chlorine or a fluorine or a bromine. Okay, they're not interested in removing an electron. What are they interested in doing? Okay, quite the opposite. They're interested in taking an electron. So, stripping an electron? No. Giving them an electron? Yes. Okay. So that's why these guys are very high ionization energy. It requires a lot. It requires a lot. It requires a lot of you, energetically speaking, to take an electron from these guys. So that's the reasoning behind that. There are some exceptions. Okay, so as trends, there is a little bit of breakaway points. Okay, there are some trends. So let's look at nitrogen and oxygen here. So here's nitrogen in the periodic table, here's oxygen. Okay, remember I told you that IE1 increases, okay, as you go across a period. For nitrogen and oxygen, and also for beryllium and boron, that trend is a little bit violated. Okay, so that trend is a little bit violated. That has to do with the electron configuration. So let's look at the electron configuration of nitrogen. So please watch that video on Friday. So the electron configuration of nitrogen is helium, 2s2, 2p1, 2p2, 2p3. Okay, so nitrogen would be helium, 2s2, 2p3. So here we have 2s, 2p, so 1, 2, 3. Okay, so that is the electron configuration of nitrogen. Okay, let's look at oxygen here. Oxygen would be helium, 2s2, 2p1, 2p2, 2p3, 2p4. Okay. Okay, 2s2, 2p1, 2p2, 2p3, 2p4. So remember our definition of ionization energy, energy to strip an electron. Okay, it turns out it's actually easier to strip an electron from here than it is to strip an electron from here. So nitrogen, in terms of our first ionization energy, nitrogen will have a larger ionization energy than oxygen. Okay, it bucks the trend. Okay, so a small violation of the trend. Okay, the violation of the trend has to do with the electron configuration. You see, removing this, and then I don't have the actual textbook values, but you see if you remove this electron, bam, you get something that's stable. You see, this is very stable. Why is it stable? Okay, what are the two P's? They're half filled. The two P's are half filled. So that's a very stable electron configuration. Removing this would actually, removing an electron from oxygen would actually give you something that's more stable. So it takes less energy to eradicate this electron, ionization energy, because you're getting to something that's stable. See, this is very stable in and of itself. So the electron configuration is just more stable. So it takes less energy to strip this electron because you're getting to something more stable. So here the electron configuration is less stable, so less energy required to achieve stability. So that's the reason why you have a little bit of a violation of the trend. Okay, same thing with beryllium and boron. Same thing with magnesium and aluminum. Okay, so there are some violations. That's all I'm saying. Okay, so the electron configuration is less stable, less energy, because after you remove this electron, you become an electron configuration that's a lot more stable before. All right, the final 4 or 5 minutes I want to talk about something that's important, and that is electronegativity. And that will be really complete all that I want you to know for Chapter 8. Before we go to something that's kind of fun, in my opinion, Lewis structure. So electronegativity is like a vacuum cleaner. Okay, electron sucking power. Okay. Okay, electron sucking power, like a vacuum cleaner, the ability to pull electron density. The ability to pull electron density. So here for electronegativity, I request you guys to learn a couple of elements here. Oxygen. Okay, oxygen, definitely all the halogens. Nitrogen. Maybe phosphorus. Yeah, but I guess that's all. Okay, so all the halogens, fluorine, chlorine, bromine, iodine, nitrogen, and phosphorus. I want you to know these, bless you. I want you to know these as electronegative. They're going to pull. Okay, they're going to pull. Okay. Okay, so when we talk about the sucking power, the ability to pull from a bond, electron density, these guys in this region are pullers. Okay, why do they pull on that electron density? Okay, these guys, like vacuum cleaners, are going to suck electron density, pull electron density, because they want to achieve nobility. Okay, instead of grabbing an electron, they'll pull. They'll pull at the electron. And it's a very, very strong pull. Okay, that very, very strong pull is called electronegativity. And we're really, really talking about this region of the periodic table. Okay, this region of electronegativity. The best example of this is water. Okay, water is H2O. Okay, this is the covalent structure of the water molecule. Okay, here we have a covalent bond between hydrogen and oxygen. Is that not correct? Hydrogen and oxygen are forming a bond. But what I want to tell you, and this is important, is that this is not an equal sharing bond. Okay, if we have a bond between Antonio and I, okay, he's a lot stronger than me, he'll pull. He can pull, okay? He'll pull. So this oxygen, because it's electronegative, it pulls. So I'm going to draw an arrow, make sure the arrow has a little tail. It pulls. It's not a 50-50 bond. Don't think we're sharing. Okay, you're getting more. Okay, because you're electronegative, that's why. Okay, same thing on the other side. It's pulling. Okay, this is not a 50-50. Okay, it's pulling. So when it pulls like that, because oxygen, fluorine, nitrogen, phosphorus, all of these electronegative elements are so electronegative, this is called electron affinity also. Electron affinity. The pulling power for these elements is so strong that water, okay, this oxygen atom in water, I'm going to put the Greek symbol for delta. This water molecule has a partial, not a full, partial negative charge. Okay, from this end and also from the other end. If that has a partial negative charge because of the pull, electronegativity, what about these two ends? What will they be? Partial positive. So within the water molecule, you have an end that's partial positive, two ends. Partial positive. You have a center that's partial negative, and that's very powerful. Okay, that's very powerful because the partial negative can do what? It can attract to a partial positive. It can attract to another positive. Okay, this is called hydrogen bonding, a very special type of attraction. But it only happens because you have electronegative elements. Oxygen, fluorine, chlorine, bromine, phosphorus, nitrogen. Okay, these are literal vacuum cleaners. So don't think of this as a bond. Okay, it is a bond actually, but it's a bond that's not 50-50. It's not really sharing. Okay, this oxygen dominates this electron sharing. This oxygen dominates the electron sharing. Okay, that is electronegativity, and these are the elements I want you to know as being electronegative. Okay, we also call this, for those of you that are taking Chem 2, okay, we also call this a polar molecule. Polar. Because the electronegativity gives it a partial negative side and a partial positive side. So I will see you all, if I don't see you in lab, I'll see you next week. Please get ahead. Okay, so since our time is limited, and we're really wrapping up the course. Next week we're hitting the Lewis structures and we're hitting it hard. So, definitely come to my office hours or see me on Zoom. Thank you.